This video is an introduction to related rates. It's an important topic in Calculus 1 and Calculus 2. The basic ideology behind this topic is we're finding a rate which is asked of us in a question. So one concept which is important to understand is that the derivative of anything is essentially the rate. So say for example the derivative of x is equal to the rate of x. Okay, so that's an important concept to understand. Moving on, let's go to our first practice question. Before we go to those questions, one thing to note is that the first step is finding a equation or formula that includes all of the variables that is given to us in the question. So let us see in the first question. A spherical balloon is being inflated so that its volume is increasing at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the radius is 10 centimeters? Breaking this up, we see a balloon. So this spherical balloon, it's being inflated, right? And its volume is increasing at a rate of 100. So like I said before, the rate is essentially the derivative of what? Of volume, right? Because the volume is increasing at a rate of 100. So you can write the derivative of volume, V is for volume, right? I've taken V as volume, and the derivative volume with respect to time. Why time? Because it says per second. So I know its volume is increasing by this much per second. So the derivative of volume is in respect to time. And that's equal to, what's the rate equal to? 100. It's important to pay attention to this word, increasing. If it were decreasing, it would be negative 100, right? So decreasing is negative and increasing is positive. So right now it's positive because it's increasing. Moving on, how fast is the radius of the balloon increasing? So what are we finding? We're finding how fast is the radius of the balloon increasing, right? Even though the word rate is not included here, we can assume that it is how fast is the rate at which the radius of the balloon is increasing, right? It's essentially the same thing. So since it's asking us the rate at which the radius is increasing, you can say the derivative of radius, r is radius, with respect to time, is equal to, we're solving for it, right? And it also ends off by saying radius is 10 centimeters, when the radius is 10 centimeters. So you can say r is equal to 10, right? Now, like I said before, our first step is to find the equation or formula that includes all of the variables that the question gives us, right? So what equation or formula contains volume and radius of a spherical balloon, right? This balloon. We can say the volume of a spherical balloon. Like, what is the formula for a volume of a sphere? If you recall, that's 4 over 3 pi r cube. That is the formula for the volume of a sphere, right? So it includes our volume and it includes our radius, right? Two other variables which are given. Our second step is to take the derivative, as always, take the derivative of both sides. So, differentiating both sides, you get dv over dt. So you ensure taking the derivative with respect to time on both sides, you get dv over dt equals, use a power rule, bring the 3 to the front. So 3 times 4 over 3, 3's cancelled out, so we have 4. Pi is a constant, so we leave it alone. And r square, because we subtract 1 from the power. And then don't forget to write dr dt, right? So we add that on both sides. Let's plug in our values. Third step is plugging in our values, right? So dv over dt is 100, and then r is 10, right? And then we're solving for dr over dt, right? So from here it's easy, we can say dr dt equals to, we can bring 10 to the power of 2 is 100, so we'll take this to the left side. So right now it's being multiplied, right? It's being multiplied, so we divide 100 by 100, so 1, right? 1 divided by 4 pi, so the dr dt is 1 over 4 pi. 1 over 4 pi watt, we need to add units, right? How fast is the radius of the balloon increasing? How fast is it increasing? Since we're using centimeters, right, the radius is in centimeters, right? Not centimeters square, because it's not the area, and it's not centimeters cube. It's not cubic centimeters because it's not the volume. It's just the radius. So we can say it's increasing at a rate of this much centimeters per what? Per second, right? So this will be the answer. Okay, easy. We'll go on to our second practice problem. The height of an isosceles triangle is decreasing at a rate of 8 centimeters per minute, while its area is increasing at a rate of 15 centimeters square per minute. If at that moment the area is 50 centimeters square and the base is 5 centimeters long, how fast is the base changing? Okay, so before moving on to the first step, what we need to do is write down what we have. Breaking it up, we get the height of an isosceles triangle is decreasing at a rate, right? At a rate of 8 centimeters. So since it's at a rate, we can say the derivative of what? Of height, right? Because the height is decreasing. Height is h, right? We take the variable h, dh over dt, because we differentiate with respect to time. That's equal to 8. Is it positive 8 or negative 8? It's negative 8 because it's decreasing. So that is negative 8. Moving on. While its area is increasing at a rate of 15 centimeters square per minute. So a rate, right? A rate, its area is increasing at a rate of this. So we can say the derivative of area, which is a, with respect to time, is equal to increasing, so positive 15, right? Moving on, if at that moment the area is 50 centimeters square, 50, right? Because the area is 50 centimeters square, and the base, b is base, denoted by base, 5, how fast is the base changing, right? So even though rate is not explicitly written, we can say, like, how fast is the base changing? We can say that, how fast is what's the rate at which the base is changing? How fast is the rate at which the base is changing? It's the same thing. So we can say, since it's a rate, we can say dB, because the base, it's asking how fast the base is changing, derivative with respect to time, and that is what we're finding, right? That's what we're finding. What's an equation that contains our height, our area, and our base of an isosceles triangle, right? We can use the area of a triangle, right? The area of a triangle is equal to half B H. Right? That's the equation of the area of a triangle, right? That's a formula. And that's step 1. Now step 2 was differentiating, right? But before we take derivatives on both sides, we need to look if we have the values of each of these. We have A, we have B, but H is missing, right? So before we differentiate, we should find the value of H. We can find the value of H because we know the rest, right? So A is 50. Step 2 here will be finding H. So 50 equals half times what is base 5, right? And then H, right? So H is, algebraically, it will be 2.5. 50 divided by 2.5, that's 20, right? And so if H is 20, we can move on to our third step, which is differentiating, right? Both sides we differentiate, so with respect to time. So dA over dt, dA over dt is equal to, here we need to use a product rule, right? If we're differentiating, so we do 1/2 B product rule, take this part and then multiply it by the derivative of H, which is 1 dH dt, plus this part H and the derivative of half B, which is what? It is just 1/2 times dB dt, right? So now we can plug in our values. dA dt 15, plug in our values, right? 15 equals 1/2 B, which is 5, dH dt, which is -8, H, which we found it to be 20, right? So 1/2 plus 20 divided by 2 is 10 times dB dt, which we're solving for, right? So now we can, do it algebraically. We can multiply 1/2 by 5, which is 2.5, and multiplied by -8, that's -20. Bring it to the left side, so this is -20, so -20. We can bring it to the left side and we get 15 plus 20, right? And that is 35. 35 equals 10 dB dt, right? Easy now, divide by 10 and you get dB dt equals 3.5. 3.5 watt. We need our units, right? What's the question asking us? How fast is the base changing? This is the base, this is the rate at which the base is changing. This is the derivative of the base with respect to time, 3.5, and everything is in centimeters, so we can say centimeters per minute, right? Per minute. So this will be the answer to this question. Moving on to our final question. A 10-foot ladder is, let me make the diagram as I'm explaining. A 10-foot ladder is leaning against a wall. This is the wall. This is the ladder. The ladder's bottom is being pulled away from the wall at a rate of 2 feet per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, breaking this up, we know 10-foot ladder against a wall. It's a good diagram. The ladder's bottom, this part is being pulled away at a rate of 2 feet. At a rate of 2 feet. We can split this up into a Cartesian plane. This is our x-axis, y-axis, and three-dimensional can be our z-axis. Easier way to look at it is that it's a distance, so it's x. So you can say that if the bottom is being pulled away from the wall, the distance is increasing, so it's a positive 2, not a negative 2. So we know the derivative of dx dt with respect to time is equal to 2, right? Because the x-axis is increasing at a rate of 2 feet, right? The ladder's bottom is increasing at a rate of 2 feet per second. How fast is the top of the ladder sliding down the wall? This is the y-axis, right? So we're finding the rate at which the top of the ladder is sliding down the wall. That's what we're looking for. When the bottom of the ladder is 6 feet from the wall. So this value is 6 feet, right? 6 feet. Now, I don't know if you can see it, but this looks like a right-hand triangle, and we can use Pythagoras theorem to find this length, right? So we can say this being z, this x-axis, y-axis, and we can take this as being the z-axis or z-axis. So we can say z square equals to x square plus y square, right? Pythagoras theorem. We're not using a particular formula, but this is an equation we can use. So solving z equals 10, 100 equals x is 6, 6 squared is 36 plus y square. You can say that y square is equal to 100 minus 36, which is 64, right? Y is equal to square root of 64, which is 8. Actually, it's plus or minus 8, but it is positive 8 because length can't be negative. So we can replace this as 8, right? Now what we need to do is, since we have all our variables, first step was finding the equation, and then optional second step was making sure we have all the variables. We have x, x is 6, z is 10, this is given to us, and using the Pythagoras equation, we knew that the y-axis, this length is 8, right? And we're finding dy dt. So differentiating both sides of the equation, we get, put this here, 2z dz dt equals to 2x dx dt plus 2y dy dt. As you can see, there is a 2 on each term, so you can cancel out that 2 to make our job less complicated, right? Cancel out all the 2's and then replace 10. I'll come back to this, okay, dz dt, because we don't have it right now. X is what? 6 times dx dt 2 plus y, which is 8, we calculated using Pythagoras theorem. Dy dt is what we're solving for. Now this is where a lot of students get messed up. What is the value of dz dt? The rate at which the length of the ladder is changing, right? Because this is the length of the ladder. But this value never changes, right? It's a constant. So the rate at which it's changing is 0, right? Because it's not changing. The rate is not increasing, it's not decreasing. The length of this ladder will always and will be 10. So it's not changing, so the rate is 0, right? So 10 times 0 is 0, equals to 6 times 2 is 12, plus 8 times dy dt, right? Now solving for dy dt, no, third step was actually plugging in the variables. We get negative 12 equals 8 times dy over dt, and dy dt is equal to negative 12 over 8, which is also negative 3 over 2. Right? Negative 3 over 2. What are the units? Standing down the wall on the bottom is 6 feet, 10 foot, 2 feet. So you can say it's decreasing at a rate of that much feet per second, right? Second. So you can say that's the answer. And how do we know this answer is correct? It's negative 3 over 2, right? And that makes sense because it's a rate at which the y-axis is changing, right? The rate at which the top of the ladder is sliding down the wall, right? This part sliding down the wall, and you can see it's decreasing. The distance is decreasing. If it's decreasing, we know that the rate or the derivative of the y-axis is negative. So our answer matches our value. So it's important to understand that when doing related rates problems, you need to find the correct equation or formula that contains all of the variables, and then before differentiating both sides, calculate all of the variables and then differentiate, and then solve for what the question is asking.